Okay, so you have a homework due today, right?
Yes.
And it was here, I've got it up on the screen, figure 4.19, is to complete the join method of the insert sorter, right? So, any questions?
Yeah. So when it's
Oh.
and it's sorted.
Yeah, that's a good question. So in some of the other methods that we did with our, when you completed like a function for the library, and we had a precondition, you actually had to implement the precondition.
Yeah.
Like with do the test and show -1, throw -1 if it did, do an error message, throw -1 if it didn't meet the precondition. Yeah, look, the short answer is you don't have to do that. So that, you don't have to do that. But look, if you did have to do it, what would you do? How would you do that sorted A low ... high -1?
Like a loop.
You have to do that in a loop. Yeah. And in fact, I'm going to show you, we're going to have a project where I actually test it with being sorted with a loop. But you don't have to do that. So with this, you can just, because we can assume that those other conditions are satisfied. All right, so yeah, that was a good question. So you don't have to do the throw -1 here. Good question. Any more? Is it working? Have you guys gotten it to work and then it sorts? Okay, good. Yeah. It's kind of neat how where you just do this one thing in here and you do it and boom, all of a sudden everything works. That's pretty nice. We started, when we did the heap sort, we started with this figure 4.5 and we said that there was a build heap method that happens in the constructor because it only has to happen once, so it doesn't have to happen repeatedly when we do the recursive sort. And then it follows the same merit sort taxonomy where you split and then sort the left, sort the right, and then join. And then in figure 4.23, we saw these three expressions that we can use to calculate. First of all, if you are at a node, you can calculate from your index, you can calculate the index of your parent. And the second one is, if you're at a node at a certain index, you can calculate the index of the left child with this 2 times I minus low plus 1. And by the way, that's the left child. What's the right child? What's the index of the right child? It's that plus 1. Okay? And then we also saw that there's an expression, the largest index of a node with at least one child is low plus high minus 1, the whole thing divided by 2 and the floor of that. And in this example, we saw that 50 was the node with the index, the largest index that had at least one child. Notice that 12 doesn't have any children and 13 doesn't have any children. 60 has some children, but 10 is not the largest index of the one that has children. Okay, so remember that. And then what we did is we traced through, we showed how the sift down works. And so what happens is with sift down, the precondition is every node below I satisfies the max heap property. It, is a subtree with a root node that is of a heap that satisfies the heap property, but the value at I itself does not necessarily satisfy the heap property. And if we have a situation like that, what sift down does is, when we traced it, how it goes through, and it sifts down and it brings the largest one up to where I was and down, and then what it does basically, after it does the sift down, it fixes it so that now it is a max heap, including the root where I was. Okay, and then we did this pretty detailed code walkthrough of figure 4.22. All right, and I think that's where we ended. But look, let's recall this. In the test for if child is less than high and a sub child is less than a sub child plus 1, that depends crucially on what feature of C++? Short circuit evaluation. And why is that? That's because, how does that work? If child is less than high is false, what does it do? It short circuits. So it doesn't do the test after it. And what would happen if those were switched? Suppose we said if a sub child is less than a sub child plus 1 and child is less than high, what would happen? It would do that first test first. But then it's not guarded. That child plus 1 could be outside the bounds of the array. You see how that works? Is everybody clear on that? Just want to make sure, because we're going to do this. This is a common technique that we're going to take advantage of in future code. Okay? And then, so you need to understand this very well, because like I say, your next assignment is going to be to write this in a non-recursively in a loop to optimize it. Okay? And I think that's where we stopped. So now what let's do is let's determine the worst case performance of sift down. The worst case performance of sift down. Now, we're not going to like write the recurrence and solve it and all that kind of stuff. We're just going to use our intuition here. But look, you guys, let's go back to the original part A of figure 4.24. You see our I is up there at the root of a tree. Are you with me? Now if there are n elements in the tree, how many times does this thing have to call itself recursively? You know, what's the worst case? Now the best case, you know, the 30, you know, it could go down and be like partway down and then be fine, and then it could stop right there. But in the worst case, where will it go? From the road all the way down. Now, does everybody understand the difference between worst case and not worst case? Best case would be right at it's already good. So best case would be 1. But what is the worst case? How many times does it have to recurse down? Well, if there are n elements in the tree, does anybody have any idea? Half? Well, close but no cigar. Well, actually, square root? Yeah, you know it's less than n, right? Because if there's n, the question is how far does it have to go down?
So it'd be the height of
It's the height. It depends on the height. That is very good. But now, the height. What is the height of a heap? Because what's the heap shape? You know, it's a tree, but you know they're all. You don't have like one branch going way down here.
Isn't it M11?
It's the log. That's very good.
Yeah, because it just splits into twos.
It splits it in two. Splits into two. And there are multiples of 2. So that was a very good insight. So look. So the question is, the question is, what is the height of the heap with n elements? And what did you say? It's the log. It's the log. Log base 2. Does everybody see that? Because look.
Oh, because it's 2.
Because look. Yeah. So this has 1, 2, 3, 4, 5, 6, 7. So this is like roughly. It's roughly 8. Right. There's roughly 8 nodes here, right? But 8 is what? 2 to the 3, and 3 is the height of the tree. See? So it's like n is 2 to the k, where k is the height of the tree. The number of nodes is roughly 2 to the k. So this is what? So solve this for k. Log n, right? Is everybody clear? Take the log of both sides. Take the log base 2 of both sides.
Was that like, that's like a roughly...
It is rough because what would happen, because it's also for, I mean, you see the tree, this is the worst case.
Well, yeah, but even like...
Are you with me?
Elements.
Yeah. So this is like a general principle. So if you have n nodes in a tree, the maximum number of nodes in a tree is of order 2 to the h, where h is the height of the tree. So now is everybody clear on that? So because it goes down log n, okay? Not n log n, not square root of n, not n squared, not 2 to the n. It's log. Is everybody okay? So there's more of our intuition. Okay. So now here's what we're going to do. We are going to use this sift down in 2 different places. We're going to use it to build the initial heap, and after we use it to the initial heap, we're going to use it to do the split. Now watch this. we're going to start here in figure 4.26 in A. We're going to start with that 7316284. The initial list is not a heap. Now this is so clever. Now we're going to use that computation. What is the node that has the largest index that has at least one child? Which node is that?
4.
I think it's 6. 4 doesn't have any children. Are you with me?
Or the index?
The index, yeah, the largest index, let's say that again. What is the node that has the largest index of the node that has at least one child? And the node is what? I mean, the node, it's the one, it's 6. I guess that's, well, depending on where you start, you know. It's this one.
Yeah.
This is the node that has, with the largest index, that has at least one child. Are you with me? See, look, 4 doesn't have any children, 5 doesn't have any children, 8 doesn't have any children, 2 doesn't have any children, but 6 does. So we can compute that. We have that little expression to compute that. So starting with this, what do you suppose we do? Starting with that 6, what do you suppose we do? We just sift down. And if we sift that down, if we sift down from there, we are guaranteed that that is a what? That the 6, so by the way, if we do the sift down, there, in this case there's nothing to sift, right?
So like the sift down is a heap.
So, but anyway, we sift down, and in this case it doesn't have to sift, but it calls it. It could have. All right. Okay, and that was this node 6. But now what's the node with one less index than 6? With the index 1 less than the index of 6. That's which one?
3.
That's this. So what do? Sift down this 1. Now what's this 1 going to do? What's it going to compare? The 8 and the 5 and the 1, right? So it'll compare the 8 and the left child, right child, blah, 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 right?
Pick 8 and I'll switch it.
And it's going to sift down, and 8's going to go up. Is everybody clear on that? Okay? So now at this point, so check this out. So here's the 8 here. So now what do we know? We know this one is a heap, the 6 is a heap. We know the one that has this 8 here. We know that that's a heap. And now what? The one with the index what? The index of 8. What's the one with the 1? What is the node that has an index that is 1 less than the index of the 8?
3.
The 3. But now what do we know about the 3? We know that the left child is a what? Max heap. And the right child is a what? Is a max heap. Yeah, because it doesn't have any children, so it has to be a max heap, right? So what do we do now? Sift down the 3. But how do we sift down the 3? Look how cool this is. Isn't this clever? So we compare the 6 and the 2. 6 is bigger, and what happens?
6 and the 3 switch.
The 6 and the 3 switch, but then we compare the 3 and the 4, and what happins?
4 and the 3 switch.
Does everybody see that it does that? All right, and so now in part D of the figure, what do we know? We know that the left child, the left child and the right child are both what?
Max heaps.
Max heaps. And so now, what is the node with the index 1 less than the index of the 6? That's a 7, and we can do what?
Switch it.
Sift down. So now we compare the 7, the 6, and the 8. What goes up? The 8 goes up, and then what? The 7 and the 1 and the 5, and? It can stay right there. And so boom, and sift down this. All right, is everybody clear about this? So now what have we done? We have done what? We have built, well, it's not in order, no. It's 8, 6, 7, 4, 2, 1, 5, 3. It's not in order, but it is a what? It is a max heap. We just did build heap. Are you with me? That thing that we have to do at the beginning. Now, is that clever? Yeah.
So are these heaps ever used outside of just trying to sort?
Actually, they are. There is a data structure called a priority queue, which can be used, which is a variation of this max heap idea. And so yes, they are. We are using them here to sort. And the data structure itself is just the array. We are just interpreting it as a binary tree.
Okay,
So that we can analyze it this way.
So let's say you do have the data structure, then how would you like find a number in it?
Well, it all depends. Yeah, that's a good question. See, every data structure, what is a data structure? I think we talked about this on the first day.
Way to, like,
It's a way to store and retrieve information. So the question is, what kind of operations do you want to be able to do to store, and what kind of operations do you want to be able to do to retrieve? And so with a priority queue, there is, if you want to store your information in such a way that you always want to have something with the highest priority, it'll always be at the root. So with a priority queue, you say, oh, that's the one with the highest priority. And then after you pull that out, the size of the heap is decreased by 1, so you take the one at the bottom and you put it at the top, and then you sift down, and then boom, that's the priority queue still. So if you always want to be able to access the maximum one. But you see, it depends on the operation that you want to have. See? So the answer is, yeah, this is used we are using it here just to do the heap sort. All right. And what we've done here so far is we have done the initial build max heap, build heap. Is everybody clear? So check this out. In figure 4.21, now we have some code. And this is, notice that we have heap sorter, colon, public A sorter. Now what's that C++ colon mean? Inheritance. Okay. Everybody good with that? And now we have, and now look, you guys, we have a constructor. We have heap sorter is the name of the method. See, it says public heap sorter, and heap sorter is the name of the method. It has the same name as the class, and it doesn't have a return type, so that makes it a what? Constructor, a C++ constructor. And here we have our virtual void split and virtual void join, and these are override, so we're overriding. And check this out. Do you see now that here is the code for the constructor? And this code for the constructor does exactly what we just looked at. Now, can you understand how this works? Do a real detailed code walkthrough here. So the post condition is that A between low and high is a max heap. And what does it do? It says for int I gets what? Low plus high minus 1 divided by 2. But we know that is the what? The index, the largest index with at least one child. Because we don't have to start, we can start like roughly halfway through, you see. So we don't have to start with the ones that don't have any children, but so we start there. And then I less than or equal to low. And remember how we went down? We went from that one to the one previous to the one previous. And then what? I minus minus. Are you with me? And as all we do is what? Sift down A between low and high. And then I is the one that we sift down from. So sift down has four parameters. The array, the low, the I of where you want to sift down from, and then the high. And there it is. Look how simple that code is. But that's because we do sift down, and so that makes the initial heap. Yeah?
Can you explain what low plus high minus 1 over 2 is one more time?
Yes, it's this. Here in figure 4.23, it's this.
Index. Okay.
You see, this is in the code. This expression is in the code. Are we good?
Yeah.
Yeah.
And does it matter that, like, what if that was like a 0.5?
Well, do you remember what C++? What does C++ do
Truncates.
when you do divide by 2 and they're integers? What does C++ do? It drops the So it does it for us automatically, so we don't have to call a for function, because that's integer division in C++. What are the three options? Just kidding. Okay, so look, so you see, now this happens only once. This is a constructor. This happens only once. This doesn't happen during the split. Now, let's think about the worst case performance to build the initial heap. So here's the code. So now what do you think? Because each time we do a sift down What's the performance of the sift down? Log n. So the performance of the sift down is log n. And how many times do we do the sift down? Yeah, actually n over 2, but n over 2 is big theta of n.
Okay.
Are you with me? So therefore, what do you think it is? Was our intuition tell us that it is? It's, yeah, that very good. You guys are getting good. So the loop executes n over 2 times, and each time, worst case, log n execution. So the t of n, the time to do it is big theta of n. So this we need to be able to do now. This is a tool that we have that we can. Is everybody clear? Any questions about this? So that's to build the initial heap. Now actually, you can show, I don't do this in the book, I don't take the time to do this, but you can actually show that the actual performance is t of n as big theta of n, because look, first of all, you're only starting, as you decrease, you know, you're not, I mean, sorry, when you start, you're not doing n, you're just doing a very small, you're doing a fraction of log n. You see what I'm saying? So I mean, it gets kind of complicated, but you can actually show that t of n is big theta of n. But as it turns out, well, let's just note this, that you could do this, that you could show this if you were so inclined. Okay, so now the question is, we've got that initial heap built. Now how do we actually sort? Now how does the heap sort actually work? Now this is really clever too, because guess what we're going to do? We're going to use sift down again. Now watch this. So here is the initial heap. Now let's verify that this is the initial max heap that we built in the constructor. 8 is bigger than 6 and 7. 6 is bigger than 4 and 2. 4 is bigger than 3. 7 is bigger than 1 and 5. So this is the one that we built. So we did this once, right? Now look, you guys, how clever this is. We have said on numerous occasions before that, what do we know about the root? The value of the root is the biggest one, because it's a max heap. So where does the root belong? Sorry, where does the 8 belong? It belongs where the what is. Now remember, this is stored in an array. Remember, this is stored in an array, and the array, and it's 8, 6, 7, 4, 2, 1, 5, 3. So my question is, we know that the 8 is the biggest one. It belongs where where what is? Where the 3 is. So guess what we do? Yeah, so what we do is we switch the 8 and the 3. Are you with me? Because remember, it's stored in an array, and the 3 is at the end of the array, is it?
Then you do it again.
Well, wait, no, we don't. Well, but now here's the thing. What has happened to the size of the heap?
It's shrunk.
The size of the heap has gone down by 1. So we no longer consider the 8 to be in the heap. Now, is everybody clear on that? So we say, okay, we have one less element in the heap, the one on the right, so we don't count that. And furthermore, what we have is a situation where the root does not necessarily satisfy the max heap property, but we know that the what? The left child and the right child do. If we don't include the 8. And so what do? We sift down. So now can we sift down the 3? What happens if we sift down the 3? It goes where? Goes to the 7, then what happens? Goes to 5, and then what happens? So the 7 went up, and the 5 went up, and the 3 goes, yeah.
Why would I mean, I'm just like forgetting, like the sift down takes into account which of the 2 is bigger?
Yes. Yeah.
The biggest one's the top.
Yeah. Yeah, that's that sift down code that we went through the other day. Okay? So is everybody clear? So now we can see what that does. So here in part C, we sift down the 3, right? But now what do we know?
It's 7.
That the 7 is the maximum of the smaller heap. So where does the 7 belong? It belongs, oh, that 3 is getting kicked over all over the place. Yeah, so the 7 belongs to where the 3 is, right? Because so what do? We switch the 7 and the 3, and now we say, aha, but now we're going to consider our heap to be 1 less in size. is this slick? Is this slick? And we're using our sit down. Okay, so now what do we know? We know that in part D, we know that the root, that the left child of the root is a max heap, and the right child of the root is a max heap. And the only thing that's wrong with it is possibly 3. So we do what?
Sift down.
Sift down. How do you sift down the 3? What happens? The 6 does what? The 6 goes up, the 4 goes up, and the 3 does what? Where's the 3 wind up?
At the bottom.
At where the 4 is. And the 6 is. Now, does everybody see how that works? All right.
Then you kick the
But now what? We know that 6 is the what?
biggest.
The biggest of this, yet again, smaller heap. So where does it go?
1.
Where the 1 is. So we swap the 6. And now what do we do?
Sift down again.
Sift down from the root of the yet smaller heap. And what's happening is the heap is getting smaller and smaller and smaller and smaller. And we just sift down, sift down, sift down. Until boom, pretty soon, no more heap. Everything is sorted. Is that slick? So let's follow it through. So now how do you do? So now by now, do you know how to sift down the 1? What'll happen?
Goes where 5 is.
It'll go to the 4.
No, 5.
Oh, sorry, 5. You're right. So that's the 5.
And then the 5 will jump to
And now the 5 goes to where?
The 2.
To where the 2 is. So we switch. So, and now the heap only has 1, 2, 3, 4 elements in it. And so what happens with the 2?
sifts down to
Sifts down to what?
the 3 to
The 3.
The 4 and the 3. So it goes all the way down. So the 4 goes up, the 3 goes up. So the 4 goes up, 3 goes up, the 2 is here.
4 and the 2.
And now the 4 belongs where the what?
2 is.
Where the 2 is. Oh, you guys are good. And so now we have 2, 3, 1, and now what happens?
2 and 3 swap.
The 3 is 2 and the 3.
2 and the 3, swap. And now we know the 3 goes where the what?
And the 1 is.
1 is.
Where the 1 is. Yeah, so we swap the 3 and the 1. And now what?
You sift down.
Sift down. And so the 2 and the 1. Switch where this is. And what is it? We're done. Actually you sift down the 1, but and now look, 1, 2, 3, 4, 5, 6, 7, 8. Is that clever?
5-year-old can do that.
Well, I mean, this works for 10 million elements, you know. All right. So look, here is the split. Now let's see if we can understand this split. Oh, by the way, let's take a look at the join first. It's easier. There's nothing to do, right? So the sorter just calls the template method calls when it calls the join, it just returns. Okay. So now what is this? So now what does this split do? We do type T. That's our C++ template type. Temp gets A sub high. So there's A sub high. A sub high gets A sub low. Are you with me? So that takes the low one up to there. Are you with me? And then A sub low gets temp. Are you with me? So low gets temp. And then what? We sift down. Now, what do we sift down? A. Now it's between low. Now do you see why it's low, low, and high minus 1? It's because.
Why is mid low?
That is why. The question is, why is mid low? It's like this. Do you see that? Let's go to figure 4.27a. Do you see that the 8 is at low? Do you see? It's between low. So in 4.27a, the 8 is at low and the 3 is at high. Are you with me? And so that 8, that's why. Now that was a good question. Does everybody? So it's really good that you understand this code at this level of detail. Is everybody clear on this? I just think this is the cat's meow. So sift down A, low, low, high minus 1. And why high minus 1? Because there's one less. So we're only going to do it to that one, to that part of it. And then and then in the very last thing, what do we say? We say what? Mid gets high. Now why do we say mid gets high? Because in split, is mid called by reference or called by value? It's called by reference. So the job of split is to do the split and set mid so that it can be used by the sort, and the other sort, and the join. Is everybody clear? So you see why it's high? It's because we're splitting off just that one each time. All right, you guys. Now here comes this is a little complex, but we can do it. Check this out. Here, what is the performance of heap sorter? So here is our code: sort A, low, high. If low is less than high, split A, low, mid, high, sort A, low, mid -1, sort A, mid, high, join A, low, mid, high. Now we got to look at each one of these things and think through how the heap sort works. All right? So what's the deal? What's the well, first of all, you know that if low is greater than or equal to high, that's the base case. It's just what? Big theta of what? Of 1. But what about the recursive case? What is the how long do each one of these things take? So now split A, low, mid, high. Remember what it does is it splits off that one on the right, but how does it do the split? It does have, yeah, it does have sift down in it. And what? Well, we know that the sift down itself is what? Is log n.
That's worst case.
Yeah, let's do worst case. Yeah, good point. Good point. Let's do worst case. So it does have log n in it. Well, split does have log n in it. Let's. Okay. Now you understand that the second sort does no work.
Yeah.
Are you with me? The second sort does no work because that's the one, you know, on the end. So the second sort does no work. And what about the join? The join does no work. Okay, so the join does no. So really what we have to worry about are the split and the sort. So it's kind of like this. The performance of heap sorters is like the split A, low, mid, high, and sort A, low, mid -1. Are you with me? And so what did we say the split has in it? It has a log n in it. So what is the time for split? It's big theta of log n. Are you with me? And then what about the sort? How many times does this big theta of log n execute? Well, it depends on how many what? It depends on how many times. Well, when we do sort A, low, mid -1, that's -1, -1, -1, -1. That's like a what? A loop that gets executed what? N times. Are you with me? So the answer to how many times does it execute is its big theta of what? N. I mean, how many times it executes is n. But in each execution of that, there's this big theta of log n. Now, is everybody clear? So it's what? Yeah, so that's big theta, and so the time for the sort is big theta of n log n. Now, is everybody clear on that? But wait a minute, that's the time for the sort. What about that initial build heap? Well, no. I thought I don't think it was log n. No, I don't think when we analyzed the build heap. What did we say?
Was it n log n?
Yeah, it was n log n, wasn't it? Okay. So the performance of the heap sorter is the time to build the initial heap plus the time to sort, right? Is everybody? Well, the time to build the initial heap was big theta of n log n, and then the time to do the sort is big theta of n times the big theta of log n. So basically what this is, but the big theta of n times the big theta of log n is like big theta of n log n. So basically what we have is a big theta of n log n plus another big theta of n log n. But 2 times big theta of n log n is what? Big theta of n log n. So that is big theta of n log n. Are you with me? Now what did we say about that initial build heap? We said if you were so inclined, you could actually show that would be what? assuming the tighter bound to build the initial heap. What did we say that initial one?
Oh,
Yeah, we said it could, we said, well, yeah, I mean, it's actually n. But look, even if we do make it n, what is big theta of n plus big theta of n log n? That's big theta of n log n. Now, is everybody clear on that? Okay. See, yeah, here. What we're saying is this: big theta of n plus big theta of n log n equals big theta of n log n. And why is this? Well, you can think of this as being a function that has a, some constant times n log n plus some other constant times n plus some other constant. And this is a function that has some constant times n plus another constant. But then these functions together, if you add them, if this happens and this happens, that's just a constant with times n log n plus another constant times n, because you can combine those two n's. And you see? So this is big theta. So look, even though, why go to the trouble to prove that the initial heap is really big theta of n? It doesn't change the final answer anyway. See, so you could do that, but why bother? See? So does everybody see then that even with that initial, even not assuming that tighter bound to build the initial heap, it is big theta of n log n, the performance of the heap sorter. Yeah.
Why did we write it as?
Because this is the way it's always done. But, yeah, what would it be? Actually, that's a good question. What would it be? I've never had anyone ask that before. If t of n, here, if t of n, here, this one, the sort A low mid minus 1 is t of what?
N minus 1.
N minus 1. But now this is what? Plus what? No, the split is log n, right?
Yeah.
Oh, I see. And this is big theta of 1, right? I'm going to have to go. See, the solution, if this were t of n minus 1 plus big theta of n, that would be, the solution to that would be n squared. This has got to be big theta of n log n. I need to put an exercise in the back of the book that has an example of proving that the solution of this is big theta of n log n. I wonder if that's a very difficult exercise to do. Here's what we have done so far. We have analyzed in detail 5 different sort algorithms. And we have all this theory, right? So what would it be nice to be able to do? It would be nice to be able to compare our theory with what? Some actual what? What do you compare that? What do you sign? You got some physics majors in here? Yeah.
Test it out.
Yeah, in practice. Test it out. Are you with me? So how do computer scientists, how do engineers, software designers, software developers, if this is a science, then we've got theory and we've got practice, right? So what we're going to do in computer science, a lot of times what the practice is we actually figure out we actually measure how fast it takes, how long it takes to do these programs and see if it matches the theory. So the question is, so the topic then in this next section in chapter 4 is performance metrics, which means the way that we actually measure the performance, and then an object-oriented design pattern called a decorator pattern. And so here, in this next slide, we have summarized the theoretical asymptotic bounds of these 5 sort algorithms. So we have the merge sort is n log n. The worst case quick sort is big theta of n squared. The best case quick sort is big theta of n log n, but we didn't do this in the book, but it's possible to show you that, because remember, the quick sort depends on that random number generator. Okay? So if in a truly random if the number generator generates truly random numbers, then you can show that the average case quicksort is big theta of n log n. And then we saw that the selection sort is big theta of n squared, the insertion sort is big theta of n squared, and the heap sort is big theta of n log n, which is what we just saw. Okay? So, the question is, how can we measure the performance? Now, what we're going to do is, we're going to show 3 different metrics. Now, do you guys know what the word metric means? A standard of measurement. No fair peeking. Okay, a metric is the standard of measurement. So what's the metric for how hot it is? The temperature.
Yeah.
How hot is it? Well, the metric is the temperature. See, that's a number. You put the number on it. Man, it's hot today, or it has been. Like it was in the hundreds. It was over 100 yesterday. Well, the metric is the thermometer, is the temperature. That's the metric. So what is our metric? What is our metric for measuring the performance of an algorithm? Well, you could have a little stopwatch and press run but what's the problem with that?
Humans.
Yeah, human error, so lots of inaccuracies. So here's what we would like to be able to, what we would like to be able to do would be to do a statement execution count. All right, so that'd be one way to do it. And that would be good. It turns out to be a little more difficult to do a statement execution count of the whole algorithm. It's easier to have the statement to have a count of 3 different things. First of all, we could count the number of array element comparisons. Second of all, we could count the number of array element assignments. And third of all, we could count the number of array element probes. Now here's what each one of these means. In this code for the heap sort, we said there was a statement if a sub I is less than a sub child. Remember that? So you see that less than? What we could do is we could count how many times the less than test executes in the sort. Total number. There's a way to actually get that number. So we can that's one element comparison. Now, what else is there here? There is an a sub I and an a sub child. Right? Now each time you do an a sub something, what are you doing? You are probing the array. You're going to that element of the array and probing it. And then a sub child, you're probing sub child and you're probing that. Do you see what I mean? So there is a way, we're going to have some software, there is a way to actually count how many times you do an a sub I and an a sub I in the code. That's called a probe. Are you with me? Do you have a question?
Yeah, what do you mean by probe exactly?
I mean, here's what it means. Anytime you execute an a sub something,
Okay.
that's a probe. You're probing the array.
Okay.
So if this executes, if a sub I is less than a sub child, there's a way to count. That's 2 probes.
Okay.
If you say if a sub I is less than key, that's 1 probe because a sub I is 1.
Okay.
Yeah.
Like if you wanted to do a sub I equals a sub child, that's 2 probes as well, right?
Yes.
Even.
Yes. Yes.
Got it.
Okay. And then another metric is to be able to count the number of element assignments. So for example, if you have a sub mid gets a sub j, that's 1 element assignment. So you could count how many times elements are being assigned. Yeah.
Probing them?
And this would also, good point, this would also be 2 probes. Are you with me? So here's what we're going to do next time. Next time we're going to demo a project, and we are going to have software that actually does this for us automatically. Automatically with the code that you wrote, because you're writing. Which one did you do last night, or are you doing tonight? Insert. So it's going to, when you have these statements in your insert, it's going to be able to go count all these, and then we're going to take some data. All right, good deal.